For today's. So again, quick, once the stress of the bottom fibers of the concrete beam is going to be approaching 7.5 square root of F prime C, the concrete beam is going to start to crack at the bottom. F prime C, it has to be in P psi. And this is the reason that when I give an example, I said 4,000, it needs to be P psi. I cannot use it as K psi in this case. And 4,000 is just a number that I throw there for sake of discussion. Now, the concrete strength is going to be specified by you, or it's going to be given to you in the problem. All right, here's the stress distribution. And they have this question about, should we use Y or should we use C? If you're interested in the stress at any level, so let's say that you are going to be interested in the stress right at this point here, this amount of stress at the height of Y. In this case, your equation is going to be including Y. To get to the maximum stress, whether you go on the top or the bottom, and instead of Y when it goes to max is going to be equals to C. So here's Y, your variable. And for maximum stress, top or bottom is going to be equal to C. C is going to be here lowercase, not the uppercase. Just, you know, C as lowercase is going to be a dimension. C uppercase is going to be a force. As you see here in the bottom picture, I can integrate this stress, and integration here in this case, it means to find the volume of the stress distribution. And once you do this integration, you're going to be finding the C or the tension. C is going to be compression force, T is going to be the tension force. And this is going to be equal to the volume of this block. How this is done, you're going to say, well, I have B multiplied by H over 2, which is C in this case, right? 1/2 of the height, multiplied by the stress, divide by 2. Why divide by 2? Because the area of this triangle face that I'm looking at, is going to be equal to the maximum stress times H over 2, which is C, divided by 2, and then multiply this by the B, the width, and with that, you're going to have the big force C, and of course, T is going to be the same as T. You need to have equilibrium. Equilibrium means summation of the force in any direction is going to be equal to 0. This is going to be the general equilibrium equation. So if you say summation of the force in this direction here equal to 0, you're going to see C is going to be equal to T, which makes sense. There is no other applied external force in this direction. I don't have any axial load. This is just a beam exposed to flexure, as it says here, flexure, right? And the external moment that you apply, you can resolve it into two components, as it says here, right? You're going to have the C and the T multiplied by the distance, which is called here JD. Some people would like to call it Y sub CT. So here's Y sub CT. What does it mean by Y CT? It means the Y, the distance from the compression to the tension. Just to make it simple for you guys. So some people call it JD, some people call it YCT. Both of them are acceptable engineering wise. So if I take here the moment about 1 point, how do you take the moment about 1 point? You go here and then you take the moment about this point on the tension. So the moment is going to be equal to C multiplied by this distance, which is YCT. Also, when you think about any couple here and then you have the distance is called YCT, the moment is going to be equal to one of these two forces multiplied by this distance here, which is the couple. This moment is internal moment. So let me confirm this again. This is what I call here internal moment, right? I'm going to call this internal moment. All right, so where's the external moment? Do we have external moment? I'm going to say, yeah, here's the external moment, the applied moment. So in this case, the external moment is going to be equal to the internal moment. And this makes sense because you need to satisfy this equilibrium, right? Internal moment is going to be equal to the external moment for equilibrium. So the internal moment is going to be T or C. They're equal to each other in value times the YCT. External moment is going to be just the moment that you calculate. How do you calculate the moment? If I give you some load, you can find out the moment diagram, and at your section of interest, and let's say the maximum point of moment, just take the moment, which is this M, right? And if you wanted to see how much force is developed within the beam, just take this moment, set it equal to the internal moment. So in this case, you say M equals C times YCT. This moment is going to be known in this case because you calculate out based on the given moment diagram or calculated moment diagram. And this YCT is going to be fixed. Why? Because where's the point here where the force is going to be concentrated? You're going to say the force is going to be concentrated, right? If you like to put it this way, at 1/3 from the base of this triangle, which is right here. It's going to be 1/3 of this base. So if the base here is going to be equal to C, this is going to be equal to 1/3 of C, and this is going to be 2/3 of C. So this distance, JD or YCT, is known to you. You can figure it out based on the section properties, height and width. And so if you take this moment here, say it's going to be equal to YCT times C. So I'm going to put here my equation. I'm going to say the moment, which is external moment, is going to be equal to C or T. I'm going to say equal to C multiplied by YCT. This moment I have it. I just calculate out. This YCT, I can figure it out based on this dimensions given to me of the section. In this case, I should be able to figure out this force C. So there's a way to figure out this two forces if you like to. There's a way of doing it by doing it that way, or you can just find out the stresses, right? So you have here two ways of doing this analysis. So the first method here is called the Flexural Formula, and here's the Flexural Formula, which is this one that we have also seen it in the 301, if you guys recall. And you set the stress at the bottom, not at the top. Top is going to be compression, bottom is going to be tension. You say once the stress at the bottom is going to be reaching 7.5 square root of A prime C, I'm going to call this moment to be the cracking moment. So the cracking moment is going to be like a limited state. It's going to be a value specific to this given concrete section or concrete beam with this strength, with this dimensions, given dimensions for the section, for the cross section. You should be able to figure out here what we call here the cracking moment. Cracking moment is not used for design. So I want to be sure that you guys understand this very well. What we're talking about here is not for a design case. This is not how we design beams. This is to understand the performance of a beam. So the purpose of this uncracked analysis for a given beam section is to understand the performance. But actual design, I'm going to put some reinforcing and the beam is going to be cracked at the bottom. All right, so I want you guys to remember this. What we are doing here is not for a design. This is to study the performance of the concrete beam before cracking and right after the cracking point. So, okay, we went through this. We say here's the moment of inertia. I can do it for a T section. Now a T section is going to be a bit complicated. Rectangular section is simple, right? Because the stress top and bottom is going to be the same. And of course, the two forces is going to be the same. And the neutral axis is going to be right at the mid height. So you take this h over 2 and the bottom is going to be also h over 2. For a T section, the centroid is going to be here. So we'll look now at the new neutral axis location, right? It's going to be shifted a little bit above the center or the mid height of the beam. So let's say if this is here 24 inch, I'm expecting center of the beam is going to be at maybe 12 inches from here. Look what happened. Neutral axis happens at 15 inch from the bottom, 15 inch and a fraction, 15.33. So this 15 inch should happen instead of, if I have your rectangular section, the neutral axis would have happened at 12 inches from the bottom. Understand the reason, because you put here more material. So we say that we put here more meat, so this is pushing the neutral axis above. This makes sense. Right at the neutral axis, the stress is going to be equal to 0, which is this point. So let me zoom in. Look what happened in the neutral axis. The stress is going to be equal to 0. The stress distribution is going to be linear, which means this line here. I understand that the flange is going to be pulling this neutral axis up. It's going to be towards the flange, where you have more material. So in that case, what do you expect when you have this linear distribution and then you're going to have stress top and bottom? So I'm going to say here the stress in the top is going to be smaller than that for the stress at the bottom, because I can have this two similar triangles. And if this height is going to be smaller than this height, it means this stress is going to be smaller than this stress. I can say F in the top divided by this, and I can still call it C, because it's going to be the distance from the neutral axis of compression. I can say here F top divided by this distance is going to be equal to the F bottom divided by this distance. Now, which one is larger? I'm going to say this distance here is larger. Therefore, this stress is going to be larger. And if you have one of this stress values, you can figure out the other one easily if you have the neutral axis location from symmetry. This dimensions is just taken from an example, a solved example, right? So not all beams is going to have this 20-inch depth and or 20-inch for the stem depth and 5-inch for the width of the stem and 20-inch flange width and this kind of stuff, right? It can be different from a beam to a beam. But I just put it here for illustration, just explain what I'm talking about. In a T-section like this, first you need to find out the centroid. And the neutral axis is going to be right at the centroid. This is great. So it's going to be simple. Neutral axis location, you can figure it out based on the section properties in terms of dimensions, not on the concrete strength. Concrete strength is a completely different issue. But the neutral axis location is going to be based on this width, this thickness, and this depth, if you like, and this thickness, you know. Now, once you find the centroid, you need to find out the moment of inertia, which is right here. For a T section, you're going to have two sections. You're going to split two areas. And then for each one of them, you're going to be finding out the moment of inertia about its centroid. And then you follow this combination. This is the way that you combine moment of inertia. And you guys should have taken this in statics. And if anyone needs help with this, let me know. I can give you an example and post it on Canvas. I'd like to hear people now. Do you guys need something? Any help with this? Like an example on how to do the moment of inertia?
Yes, please.
Okay, no problem. No problem. We'll do that. Now let's say that now you have this I, which is a moment of inertia for the entire section, not just for the flange, not just for the stem, it's going to be for the whole thing. This moment of inertia is going to be moment of inertia for the section, it's written there. Y top is going to be distances, this distance from here to there. This is going to be Y top, which is this arrow, right? So let me write it here. This is going to be Y top. Y bottom is going to be from the neutral axis to the bottom fibers of the beam. Okay, great. Now let me follow this equation. The equation says F is going to be equal M divided by I times C or times Y. Where is this equation? I'm going to take you back to this guy here. The stress, whether it's going to be sigma or F, is going to be equal to the following. M divided by I times Y. M divided by I times Y. Okay, here's the moment. It's going to be the same for top or bottom. It's just one moment value. Moment of inertia is going to be one value for the entire section. If you're interested in this F on the top, what do? You multiply it times this Y top. Interested in the stress at the bottom, use this Y bottom. So I was going to say the top usually is going to be compression. I understand that. If this is going to be compression, should be negative stress. I'm going to say one of the ways that you can report stresses, you can say I have a stress here, let's say 20 psi compression. You don't really need to say negative 20. So you can just say 20 psi compression. And here's going to be, let's say 50 psi tension. So this is understood. It's going to be good enough. You don't really need to say positive and negative, right? But if you decide here to put it as positive stress and negative stress, this is also acceptable. Nothing's wrong with that. Now, based on this equation, if I take here this I divided by YT, which is this term, I divided by YT is going to be equal to S, which is the section modulus, as it says here. Top section modulus when you take I divided by YT, like in here. Same thing for the bottom, right? All of this analysis that you're talking about, it is based on this Flexural formula, which means this equation. Finding out these two forces is not going to be really the Flexural formula, but it's going to be leading to it. So finding out T and C, you can do it, but once you start to do this, you're going to have this force method, if you like. When you look here, and then you see the stress on the top is different from the stress at the bottom. Do you think I'm going to end up with the C is going to be equal to the T, to the tension force? I'm going to say yes, because equilibrium has to be satisfied. And definitely, if you run your analysis based on this given the stresses, and you find out the stress on this T section and the stress on this stem, if you do integration, C is going to be equal to T at the end. This is confirmed. I have one example here. They give you the section properties, 16 by 24. And the question is going to be about the cracking moment. Cracking moment is a limited state. We don't use it for design again. It is just used to study the performance of the beam. I have the steel stress strain relationship, which is not really critical because, as I mentioned before, the reinforcing are not doing anything before the cracking point, and you can just ignore it. And here's a compression stress strain relationship. Maximum stress is 4,000 psi, and this is what I care about. So this information is not really needed. The 3 number 8 is not needed. The 3 inch is not needed. All what I care about is going to be 16 inch by 24 inch and 4,000 psi concrete. And the ask here about the cracking moment. What's the cracking moment by definition? You can say cracking moment is the moment at which the stress in the tension side, which means at the crack bottom of the beam, is going to be approaching 7.5 square root of F prime C. Okay, good. Here is the cracking stress of the concrete. Concrete is going to start to crack at this value here, 7.5 square root of 4,000. I didn't say 4K psi and then divide the whole thing here by 1,000. Otherwise, I would end up with a complete different answer. So at almost 475 psi, the concrete at the bottom is going to start to crack. Now, where's the neutral axis location? This is here a 16 inch by 24 inch. I'm going to go back here one slide. 16 by 24. Neutral axis and the centroid is going to be right at the mid height at 12 inches. This is why I chose here neutral axis is going to be right at the mid height. I'm going to say here neutral axis is going to be right at the mid height. Stress on the top is going to be the same as stress on the bottom. And this C, which means 1/2 of the height of the beam of the depth section, is going to be equal to 12 inch. How about the section modulus? In a case like this, I'm going to say section modulus. I guess you guys maybe have seen this before. Moment of inertia, as you know, the moment of inertia I is equal to BH cubed divided by 12. How about the section modulus? It's going to be given by this equation. S is going to be equal to BT squared divided by 6. Now, section modulus for top and bottom is going to be the same, and this makes sense. Why? Because you have symmetry here, right? Look at this. Section modulus top and bottom is different. Why? Because this distance, Y top is different from Y bottom. But in my case here, it's going to be the same, 12 inches and 12 inches. So this S is going to be working for S top and S bottom. It's the same. Equals to BT squared divided by 6. The width is 16. Depth, total depth is 24 inch. Sometimes you can call it T. You can use it H as an H. It's okay. It doesn't matter. Both symbols can be used alternatively. And with that, the section modulus is going to be 1536. Based on this Flexural formula, the stress is going to be equal to the cracking moment divided by S, which is stress, the cracking stress. And this by definition is correct because a cracking moment is going to be that moment when the bottom fibers or the tensile fibers of the concrete is going to be approaching this value here, the cracking stress. So based on this equation here, I can take it. I have the S value, 1536. I have the cracking stress, 474.3. I guess I should be able to figure out the cracking moment. And here we go. Cracking moment is going to be equal to that much. Now be careful about units. This S, I have done it in inches. The stress is going to be in pound and inches. Therefore, the moment, as you know, any moment is going to be equal to some force multiplied by a moment arm. So it's going to be equal to this number here, 728,000 pound-inch. Usually, it is preferred when you report moment in kip foot. How can we do this? Number one, this is going to be in pounds. You'd like to put it in kips. How many pounds you have for a kip? You can say 1,000 pounds. Here we go. Divide this by 1,000. And now also divide by another 12 because you'd like to convert from inch to feet. So you can say if you take here 728, right? 5 to, let's say 4, divide this by 1,000 to put it in kips, divide this by 12 to put it in at the end kip foot. So if you take this beam section, regardless of the amount of reinforcement that you put there, you start to apply any loads on this beam. And you guys, you have done already moment diagram, so you know what this means by moment. And once the moment at that given section is going to be approaching 60.7 kip-foot, this beam is going to start to crack. Before that, the beam is not cracking. It doesn't mean I'm going to be designing the beam to crack or not to crack. This is not our discussion now. This is just in terms of performance. It's not about design again. This cracking issue is about the performance, how the beam is going to perform when you apply loads to it, and when do you think it's going to start to crack. Any questions? Looking for questions.
So before that 60.7 kip feet, the rebar does not even have an effect?
No, rebar's not doing much.
Okay.
Nothing. They're not triggered yet because the amount of tension that you have in the concrete is going to be the same as the tension that you have in the steel, and the concrete is still active. But once you pass 60.7 kip-foot, once you pass it, performance is going to be completely different because now this bottom is going to start to crack, and then the steel is going to be able now to take the tension, and performance is going to be completely different. Good question. Thank you. Any other questions on this issue?
What is the scale of this cracking? I mean, it can't be very big, right?
No, you cannot see this by your eye. Usually you need to have something strong, a magnifying lens or something to be able to see it. This is not the crack, like not even close to 1/16 of an inch. This is small, but this is going to be the starting point.
I see. Okay,
And
thank you.
yeah, and as long as you start to add more loads, what's going to happen? The crack width is going to get increased. It's going to get larger and larger. It doesn't mean now the beam is failing or anything. I mean, once you see here some cracks at the bottom of the beam, it doesn't mean that the beam is collapsing, right? It's going to collapse at certain crack width, at certain given load that we can calculate out. We're going to do this for our design. We have another example, given section. As you see here, I'd like to start with the picture, just easy to understand first. The beam span is 4 feet. It says here load diagram. It has 4.5 kips, like 4,500 pounds, right in the middle. 2 feet, 4 feet, and I guess you guys know how to do the moment diagram for this. The moment on this is going to be positive moment, right? Because once you apply this point load on the top, tension is going to be right here. So this is going to be the tension zone is going to be right here at the bottom, right? So we call this positive moment, and the moment is going to be acting this way. So you can find out this is going to be 4.5 kips divided by 2 and then multiplied again by 2, right? Find out the moment. Cross section, as in section here, AA, here's section AA, the depth, total depth is 12 inches, and the width is going to be 6 inches. There is no T section. It's going to be a very simple section. Now let's see here the description. It says normal weight plain concrete. There is no reinforcing. This is why it says plain. Normal weight means the weight is 150 pounds per cubic foot. There is no reduction for lightweight. You guys know, remember the reduction of lightweight lambda factor, the 0.75. I don't have it here. This is why it says normal weight. So your lambda factor equals 1. You just ignore it. The beam is 6 by 12 in cross section, as shown in this figure. This is taken from your textbook, right? So that if you like to go back and read the whole section on it. The beam is simply supported on a span of 4 feet, very small span. And this seems to be like in a test, maybe in the structural lab, and they're doing some testing. This is not an actual beam in real life. We don't do plain concrete beams in actual construction. You need to have some reinforcing. So this is just to study the performance again and to explain the topic, the subject here. Subjected to mid-span concentrated load of 4,500 pounds, assume F prime C equals 3,000 psi. So what are the questions? Calculate the maximum concrete tensile stress using the internal couple method. B, repeat part A using the Flexural Formula approach. How about C? C, it says compare the maximum concrete tensile stress with the value of modulus of rupture, which is FCR, using the ACI recommended value based on F prime C. If I like to repeat these 3 items, I'm going to say the first one, do you want me to do this internal couple method? Where's the internal couple method? We can say, yeah, find out C and T, and based on this, find out the moment. Actually, the moment is given to you, right? Look at this. The moment is given to you. But it says here, calculate the maximum concrete tensile stress, which means they want you to find out the stress after you find out C and T. This is going to be one method, the couple method or the force method. And then it says, repeat the same process, but what is the same? Not exactly the same steps, but repeat the same thing to find out the stress top and bottom, right? Using the Flexural Formula method, which is this method here. Item number 3, it says, compare this to determine if the concrete beam has cracked or not. So in this case, I need to find out what is the stress at the cracking point and see if the beam has approached this stress or not in reality. You say, okay, beam weight here needs to be included. That's why he said normal weight, and that's why I'm gonna have here the beam weight. So the weight of the beam, if you like to figure out the weight of this beam, how do you do this? You say width times the depth, and of course you need to divide this by 12, divide this also by 12, it's gonna be half times 1 foot, and I'm gonna do it here per linear foot of this beam. So it's gonna be like uniform distributed load applied to this beam. And as you see here, the unit weight of the beam was taken as, for concrete, 150. I guess we discussed this, right? We say if you don't have this information, use 150 PCF. What is PCF? Pound per cubic foot. Pound per cubic foot, right? So with that, the weight of the beam itself is 75 pounds per linear foot. So for each foot here, you have 75 pounds, right? Now this is gonna be uniform load. So with the applied moment, is gonna be based on this given load and the self weight of the beam. This is why when you look here at the equation to figure out the actual moment applied on it, it's gonna be equal to PL over 4. What is PL over 4? This is gonna be the external applied load. And what is W squared divided by 8? This is gonna be for the self weight of the beam. So I'm gonna put it right here. I'm gonna say this is here is gonna be for the self weight of the beam. What is PL over 4? You can say moment due to its external applied load, which is a 4.5 kips. It's gonna be like the maximum moment right at the midspan. Here's the first one, 4.5 kips, 4.5 kips times 4 feet. P times L divided by 4. How about for the uniform load, the self weight, 75 pounds per foot times the span, WL squared divided by 8. Now this moment here, if you notice that we are using feet when it comes to span and distances, and for the force we use pounds and pounds. So the moment needs to be 4650 pound foot. Yes, I mean, you don't really need to memorize this equation for the moment. But usually people working in the structure business, they know this by heart. It's so simple to them. But if you like to do it from the first principles, which means that you come here, find out the reaction, take the reaction times this distance, it's going to be equal to the applied moment, this would be fine, and then put the uniform load, and then do your analysis. It can take like 10 minutes easily from you. So if you know it, you can just apply this equation here. It's going to be much simpler for you. This is going to make your life easier. Usually, you're going to have this going to be for a point load at the midspan, and this going to be for uniform load, which is very common. So this one, you really need to memorize it. And it's so simple as you see here. So the applied moment, according to this analysis, for the given information, given forces, is going to be equal to 4650, as it says here, pound foot. So, okay, good. So, okay. Now the internal couple method. My understanding is, if this is going to be 6 inches, the point load is going to be at 1/3 from the base. Where's the base of this triangle? We're going to say this is going to be the height, right? 6 inch divided by 3 is going to be 2 inches. Here's the point load, compression force, same thing from the bottom. This is going to be the tension force at 2 inches. Therefore, this distance Z, or this is the same as YCT. You remember this YCT? Or some people call it JD, is the same. So you can call it Z, YCT, or JD. I'm okay with either of these symbols. I said, okay, so this Z is going to be equal to 8 inches. This is going to be constant based on this section properties, based on the depth. Now, also, I know that external moment is going to be equal to internal moment. So how much was external moment again? 4650. This is here external moment. Let me write this down. External moment. Right? Now, let's set internal moment equals to external moment. So 4650 is going to be equal to C or T multiplied by 8 inches. But you got to be careful because this is going to be here in inches and this is going to be here in feet. So you got to be careful here about units. So I'm going to say here's the external moment, M, equal to C times Z or T times Z. Any one of them. This should be fine. So here's the 4650. I'm going to multiply it here by 12 to put it in pound inch. So because this number here, again, is going to be foot pound, multiplied by 12. It's going to be equal to C multiplied by 8 inches. Now, this is going to be kind of consistent equation because everything here is going to be in inches, right? Therefore, this compression force is going to be equal to 6975 pounds, which is the same as the tension force. So with that, I was able to resolve the moment into two forces, into a couple. And this force, right, multiplied by this distance 8 inch, or this force multiplied by this 8 inches is going to be equal to the external applied moment, which is right here. And we have it here in details. Here's the force, 6975 pounds. So what do you do after this? I'm going to say, let me take you back here to one picture before I go back here to slide number 12. Let me take you here. We said that you're going to be doing integration. And when you do the integration, this force, right, is going to be equal to the integration of this stress block. Now, this force, I have it because I did the analysis, now I have it. And this force is going to be equal to the stress times this depth, h over 2 divided by 2 for this area of this triangle face, multiplied by the width b. I'm going to do exactly the same thing. Now, let me go to slide 12. All right, here's the compression force. It's going to be equal to 1/2 of the stress on the top. Why 1/2? Because of this triangular shape, right? And this is going to be the area of this triangle multiplied by the width of the beam. It just happened that the width is also 6 inches. So this here is going to be B, right? The width of the beam. I'm going to write it here. And what is this 6 inch? This is going to be C. If you remember, this is going to be C lowercase, right? And what is this 1/2 of the top? This is for 1/2 of the area of this, which means the area of this triangle. Now, what is missing here? I have 6975 pounds equal 1/2 F top 6 inch by 6 inch. I guess I should be able to find out the stress on the top. The stress on the top is going to be the same as the stress at the bottom. You need to keep this in mind because this section is just simple and rectangular section. So let me look here at F on the top is going to be equal to 388, which is the same F at the bottom, 388 psi. Now, using this method of the internal couple, I was able to determine the stress on the top and the bottom to be 388. The big question is this beam now has been cracked already or did not? Right? And this is actually what you're going to be doing in item C. So I'm going to skip B and just jump here to item C since I reached the same conclusion through item B. So I'm going to say, okay, let me here check the stress. Based on this ECI recommended equation, and of course it has the lambda and it says normal weight, so my lambda is going to be equal to 1.0, 7.5 square root of F prime C. This beam is going to start to crack at a stress, tensile stress of 411. The current stress right now in the beam, due to this applied load and the self weight of the beam, is equal to 388 psi. Therefore, the concrete beam did not crack yet. And then it has here a little discussion, is going to be about 6% below the modest rupture, which means you still have maybe have 6% before it fails, before it starts to crack. Don't forget, in this case, I said before it fails. Why it fails? Because this is plain concrete. In plain concrete, concrete is gonna fail once it's gonna start to crack. Once it's gonna start the first crack, it will not show any resistance because the crack width is gonna increase and the beam is gonna be collapsing right after. If this makes sense. This is okay. Now let me see here the flexural formula approach, which is a simpler method that I have used in the previous example, in example number 1, that you find out the moment of inertia. Here's the moment of inertia, right? pH cubed divided by 12. And then you say, here's the flexural equation. If top or bottom is going to be equal to m times c divided by the moment of inertia I. Where is this moment coming from? I'm going to say this moment is going to be external moment, right? So I'm going to say external moment 4650 multiplied by c, which is 1/2 the depth, 6 inches, divided by the moment of inertia, which I just calculated out here, the 864. End up with exactly the same stress. Look at these two values. Exactly the same stress. So whether you do it with the forced method, which means the couple method, or you do it with the flexural formula method, you should end up with exactly the same number, unless you have some approximation in your analysis here. Any questions? Good. All right, now let's do a little bit more complicated example, which is a T section. And now you recognize this T section. This is now slide 14. I'm just going to go back here for a second. I'm going to be looking at this T-beam section that I use here in my analysis, right? That for sake of discussion. So actually, this is going to be the same beam. Now we're going to have all details about this T-beam section. I'm going to go forward here to T section of the slide set. So it says here, calculate the cracking moment, which means at which moment this beam is going to crack. For this T-shaped unreinforced concrete beam, there is no reinforcement. So don't worry about the reinforcement. We're just trying to find out the cracking moment. Concrete strength is 4,000. Did it say lightweight concrete? Anything about the lightweight or normal weight?
No.
Therefore, it is normal weight. So no one mentioned anything. It's going to be absolutely, it's going to be normal weight concrete. Assume positive moment, which means compression the top, tension the bottom, because negative moment means tension is going to be in the top. And you see the big difference? Stress on top and bottom is going to be different. Use the internal couple method and check using Flexural formula. What's the internal couple method? Which means find out C and T. The Flexural formula, you do the moment of inertia, which is a kind of a simpler method. Someone's gonna say, is it gonna be like the way it works that every time we're gonna be asked to do it with the internal couple method and the Flexural formula? I'm gonna say no. If I didn't mention any method, you pick the easy one for you. And most likely it's gonna be this Flexural formula. Unless I go there specific and say, use this method, whatever method I'm gonna be specifying, right? So your grade is gonna be based on performing or doing the problem using this method. Now let's look here at the problem and what's happening there. The T section, you have 20-inch flange width, 4-inch flange thickness, and then you have a stem of 20 by 5, and this can be the expected distribution of stress. Now, you'd like to find out the centroid location, and here's a very good example. Since you asked me how to find out the centroid, I'm gonna say, okay, let's go through this example here. So you have it in your slide set. We're going to be taking here location of the neutral axis. We're trying to find it out. So I'm going to say Y bar. What is Y bar? Location of the neutral axis. From where? From the bottom. I'm going to be drawing here a line. I'm going to say, here's my reference axis. You see, this RA means a reference line or reference axis. I'm going to divide this area here into two areas. This is going to be one of them, right? The top one. And here's going to be the bottom one, which is the stem one. Which is going to go in a little bit beyond the limit because the object snapped. Okay, so I have here two sections. The first section top here, if you look at it, its area is going to be 20 times 4. And the bottom one, which is the stem, is gonna be 20 times 5. So this is gonna be 80, this is gonna be 100, right? I have here 4 times 20. What is 4 times 20? This gonna be for the flange, 80, and this gonna be like the 100, right? So this gonna be A1 and it's gonna be A2. So what is A1? This is A1 and this is A2. A1, A2. You multiply this times the distance from the bottom, the reference axis, to the centroid of each one of these sections. So I'm gonna say, what do you mean? I'm gonna say, where is the centroid of this first section? You say centroid is gonna be at 10 inches from the bottom here, right? Centroid of this section is gonna be at 10 inches. How about centroid of this section? You say centroid of this section is gonna be the distance from this point here all the way to here. How much is this from here to there? You're gonna say 2 inches, right? From the centroid of this to here, plus 20. So this distance is equal to 22. And this distance to the centroid of this section is gonna be equal to 10 inches. So remember, for the stem is gonna be 10 inch, for the flange is gonna be 22. Okay, here we go, 22 and 10 inches. I guess we know where is this coming from, right? These two numbers. The distance from the reference axis to the centroid of each one of those sections. Divided by the total section area, which is 80 plus 100. And with that, y bar, the distance of the neutral axis, measured from the bottom axis. Why the bottom axis? This is going to be the reference axis. This is going to be equal to 1533. Here we go, 1533. Now I have, this is going to be your y bar. I'm good. Now I have the centroid. And this is where the neutral axis is going to happen. So I can draw here a line. I'm going to say, here is my neutral axis, right? I'm going to say here, if I'd like to put here, to find out the moment of inertia, how can I do it? I'm going to say, I have the equations in the previous slide, but also I'm going to show you how to do it here. To do the moment of inertia for this T section, you do the moment of inertia for the top section first, and the moment of inertia for the bottom section about its own centroid. As if you take here the centroid of the top section, you just do its moment of inertia the standard way you know about, which means BH cubed divided by 12. Repeat the same thing for this one also. And what do you do after that? There is a component that you need to add to it. I'm going to show you the equation. Okay, well, here it is. Here's the moment of inertia. This is shown here in the last slide, but since we're talking about centroid moment of inertia, let me just finish it. So total moment of inertia of the section is going to be composed of two components. The first one, summation of I sub 0. What is I sub 0? Moment of inertia of each one of this section about its own centroid. And where do we have that? I'm going to say, okay, here we go. I said the equation for any rectangular section is going to be equal to BH cubed divided by 12. So the first one, which means the top flange, the width is going to be equal to 20 and the depth is 4 inches. How about for the stem? Width is 5 and the depth is 20 inches. Let me confirm this. So I'm going to go back again and look at numbers. Look at this. 20 times 4 cubed divided by 12 plus 5 times 20 cubed divided by 12. With that, I have I sub 0, which means the moment of inertia for each one of these sections about its own centroid. I'm done with this. I'm going to say plus summation of AD squared. What is AD squared? A is going to be the area for each one of these sections. So I know the flange is going to be 80, right? And the stem is going to be equal to 100. So what is D? D now is going to be the distance from the final centroid, the global centroid, multiplied to the centroid of each one of these sections. Keep this in mind, 667 and 533. Let's see where is this about, or what is that about. The distance from the global centroid, or neutral axis, to the first centroid for the first area on the top. I guess you should be able to do your math. If this is going to be 15.33, you should be able to figure out this. And same thing here. Because if you take 15.33 minus 10 inches, why 10 inches? The centroid of the bottom stem is going to be 533, because from here to there is going to be 5 inches. Same thing, you can do it for the 6.67. So this is going to be your D value, right? A times D squared. Here we go. A times D squared, A times D squared. With that, you have the global or the total moment of inertia for this I section. Now, I guess centroid is clear, moment of inertia is clear for a T section, and we have very good example on it. Let me go back here. I'm going to go back to this slide and see exactly what they're asking for. They say use the internal couple method first and then check using the Flexural Formula. I said, okay. So actually for the couple method, I don't really need the moment of inertia, but I need it for the Flexural Formula. That's why I just continued and did it. I said, okay, you're asked for the cracking moment. The cracking moment by definition is going to be the moment at which the stress at the bottom is going to be approaching this value here, the cracking stress. So we said, when the stress at the bottom is going to be equal to 7.5 square root of a prime c, what's going to happen? Right? Which means when the stress equals 474, we have seen this value before, and we know it's going to be normal weight concrete, 4,000 psi. So when the stress is going to be reaching 474, the beam is going to be cracked. Now, if you know the stress at the cracking point is going to be equal to 474, how about on the top? Can you figure out the stress on the top? You say, well, let me write my equation here. I'm going to write it here. Let's say F on the bottom divided by 15.33 equals F on the top divided by, can someone help me? That's it, 6.67, or should I add something to it? Plus 2 inches. Why is that? Yeah, you need to add 2 for this. So the distance from the top of the beam to here is going to be equals to y top, right? And this is equal to 6.67 plus 2 inches. So now this equation makes sense. If I use this equation here and you have the bottom stress, because the bottom stress is going to be equal to 474, the cracking stress, you can figure out the top stress, F top. This is exactly what happened here. So F top is going to be 268. As you see here, the bottom stress is larger than the top stress, and this makes sense. Why? Because the stress distribution is linear relationship, and this stress it has to be lower than this stress. It makes sense to me. So what do you do after this? I'm going to say, well, I need to have forces. So how many forces do I need? I'm going to say, well, let me look here at the force diagram. This is going to be a very good one that you guys need to understand. The bottom, the stress looks like this, right? Stress distribution is going to be this triangular distribution. And I'm going to have one tension force. It's going to be simple because this is going to be triangular stress distribution on the bottom stem, and I have the depth of it. I have this stress. I can determine this tension force. But when it comes to compression, it's going to be really complicated because the compression is going to be like this. Just imagine the compression stresses is going to be something like this, right? And actually, it's going to be forming something complex because the neutral axis is not right at the bottom of the flange. You're going to have here 3 forces. To make it simple, you need to divide this into 3 forces. Look from the side. I'm going to go back here one slide. Look at the stress distribution. Also, look at this. Look at the stress distributions right here. So this triangle is applied over this section. How can I find out the volume for this? If you like to say F stress times the depth divided by 2 is going to give you here the area of this triangle. Multiply by 20 or multiply by 5 inch. Which weights should I use? So we're going to say it is really complex. This is the reason that I'm going to do it based on 3 forces, as you see here. I'm going to divide this based on 3 forces. I'm going to say everything that goes to the flange is going to be based on this trapezoidal distribution. Look at this. Trapezoidal distribution applies on the flange. And this triangular distribution is going to be applied on the remainder of the stem, on this piece, from here to there. For this trapezoidal, I can't really figure out the centroid of a trapezoidal. But if I have a case like this trapezoidal, maybe I better divide into a rectangle and a triangle. Okay. The first force here, because I need to divide this, now I'm going to divide this into 3 forces for simplicity. And for each force, I can find out its Z. What is a Z? Distance from the tension to this compression. The first force is going to be due to this rectangular distribution. Second force is going to be this triangular distribution of stress, and this is going to be C3. Finding out the Z to each one of them is going to be a geometrical issue that you need to work with. How's that? You have this is going to be 8.67, and this here is going to be 4 inches. Therefore, from here to there is going to be 467, right? The centroid of this 4C3 is going to be at 1/3 of this base, right? From here to there, the 467. So you take 467 divided by 3, give you location of C3. And with that, you should be able now to find out Z3, which is right here. It's going to be like geometrical work that you need to work it out. C1 is going to be at the mid height of this, of the 4 inches, which means at 2 inches from top of flange. So I'm going to be going down here 2 inches. And then with that, if you know this, you can figure out the distance from C1 all the way to the tension force. So I'm going to say finding out Z is going to be a kind of a geometry problem that you guys should be able to do it in your own. Now, how do you find out the forces? C1 and C2 and C3. C1 is going to be equal to stress distribution, which is uniform, multiplied by 4 inches, multiplied by the width of the flange, because whatever above this line is going to be on the flange, the 20-inch wide flange. Whatever that you have below this line is going to be based off the 5-inch for the stem width. So I said here, well, I'm going to have here 3 forces, C1, C2, and C3. Total force, you can just add them all together, which is going to be the same as a tension force, as a check if you like, right? So let me find out C1, C2, and C3, and let me find out here the tension force T. How do you find out the tension force? I'm going to go back here. Tension force is going to be based on this tension, right? It's going to be equal to the stress at the bottom times 1533 divided by 2, multiplied by the width of the stem 5 inches. So where is this at? I'm going to say it's right here. Here's the tension force. 5 inch, the width of the stem. 1533 is going to be the depth of the neutral axis from the bottom fibers to the neutral axis itself. 474, if you recall, this is going to be the stress at the bottom fibers, the tensile stress, 1/2 for the area of this triangle. So I'm going to take you back here just to show you this. Bottom stress, 474 times 1533 divided by 2, area of this triangle, multiplied by 5. Let me check. Yeah, 1/2, 474, 1533 times 5 inch, you're going to have 18.17 kips. Total compression force, it has to be nearly 18.17 because, you know, when you look here at the analysis, there is some approximation in calculation of this, right? Some rounding. So it ended up to be 18, which is good. Not very bad. Let's give you like the different. So, okay, good. Now I have the tension force. How about the compression force? As I said, I'm going to have here 3 forces. Where's the first one? The first one here is going to be based on this amount of stress. I know the bottom stress, as we discussed, is going to be 474. Am I correct? Please, yes or no? Do I remember the number correctly? Yeah, 474. How about the top, at the stress at the top? 268. So I'm going to say the stress here on the top is going to be 268 psi. What do you mean 268? From where to where? I'm going to say from here to here. How about for this, for C1, this red box? How much is the stress? I say the stress is going to be the stress right here. How much is that? I say, well, if you have 268 at a distance of 8.67, because look at this. The depth from here to there is going to be 8.67, correct? So the slope of this line is going to be equal to 268 divided by 8.67. So let me write this down. The slope is going to be 268 divided by 8.67. How can you find out the stress at this point here? I'm going to say, let me multiply by the distance from here to there. I'm going to say multiplied by 4.67. With that, you're going to have the stress, which is right here. How much is this? Now let me see the analysis. 468, 867, and then you have 4.67. Let me see the stress. It is right here. If at the bottom of the flange. But they did it from the bottom. It says here 467 divided by 1533 times 474. I did my analysis, if I may go here, I did from the top. Can I do it from the bottom? You should be able to, because the slope is going to be 474 divided by 1533, right? Or is equal to 268 divided by 8.67. Can someone help me and find out the slope of this line? I'd like to do the comparison, right? So I'm going to say I have here the slope of the top line is going to be 268 divided by 8.67. How much is it? Someone help, please?
30.9.
30.9. All right. The slope of the same line, but at the bottom. You say, okay, the slope in here is 474 divided by 15.33. How much is that?
30.9.
Same number. Okay. So whether you use 268 divided by 867 is going to be the same as 474 divided by 1533. And then take the slope multiplied by 467 to find out the stress at this line. I have tried here. Look at this. This is going to be the stress right there. Where is it at? Oh, it's giving the top. Look at this. Now multiply by 467, you're going to end up with 144 psi. Say, okay. Therefore, the stress right here is going to be this number, 144 psi right here. So C1 is going to be equal to the stress at this line, multiplied by the depth 4 inches, multiplied by 20 inches for the flange width. This is going to be C1. C2 is going to be this triangle, which means 268 minus 144, right? Because 268 is going to be the whole thing. This triangle is going to be 268 minus the 144 times 20 inch for the width times 4 inch for the depth, divide this by 2 because it's going to be a triangle. So I said, okay, let me go back here to the Ford distribution and figure this out. Here is C1. C1 is going to be equal to the stress which is right at the bottom of the flange. Where's the bottom of the flange? Bottom of the flange, which means this one, right? Which is the same as this one for the red box. This is what you call here bottom of the flange. It's going to be the stress here. So here we go, 144. The stress at bottom of the flange times 20 times 4. This is going to be like the rectangle. This one is going to be the top triangle. 20 times 4 divided by 2. And what is this 0.1236? I'm wondering, where is this coming from? I'm going to say this is going to be equal to 268 minus 144. Can someone help me and confirm that? Yes? No? 0.124? Is this correct? Yeah. Okay. 124 psi. Now it makes sense. So what does it mean by the stress here? If I'd like to see it on the stress distribution, I'm going to say this is stress. This is going to be the stress from here to here. From this point to that point. This is going to be the 124 from here to here. So this 268 composed of two values. The first one is 144 and the second value is, I can just do it here, it's going to be 124 psi. You add them together, you end up with 268. Here's the second force. And which force is this now? This is going to be for the stress that happens at part of the stem that goes into compression. What do you mean part of the stem? I'm going to say for this piece here. This is going to be the flange, here's the stem, and it happened in compression. This is going to be C3. I'm going to go back here also to this slide, because this slide makes more sense. I'm going to say, in this section here, in this section, what happened? I have some compression stresses over a width of only 5 inches. So I need to have the stress here, which is how much? You said we figure this out. That was 144. So it's going to be 144 times 467 divided by 2 for the area of this triangle times 5 inch for the width. So okay, 144 times 4 inch for the width, 467 times 1/2. 3 forces, you add them up all together, you end up with almost this number here. It turned to be 18.18. I have too many forces, right? How many forces? 3 forces and 1 tension at the bottom equals to it. How can you find out the moment in this case? I'm going to say the moment, if you want to do the moment, you remember I said you can just take the moment, is going to be equal to C or T multiplied by the distance. but I don't have just one distance. So in this case, I'm going to say, let me take here the moment about the tension force. Take the moment about the tension force right at this point. You're going to say C1 times Z1 plus C2 times Z2 plus C3 times Z3. And this is going to be your moment. So I said, okay, moment equals, here's the first moment, C times Z1, C times Z2, C times Z3, just add them together, this gives you the cracking moment. So you say C times Z plus C times Z plus C times Z, you just add them, is going to be equal to that value. Therefore, this beam is going to crack at this moment. And also you need to be careful about units, right? This is going to be here in kip inch. And this is to answer this question. It says here, the question is, use the internal couple method to determine what? The cracking moment. And I was able to do this with this, taking the moment about this point and do the force diagram for the internal couple thing. It's great. Can I do it? Because it says here, confirm with the Flexural Formula. You just check. The Flexural Formula is so simple. Look at this. The Flexural Formula, it says the cracking moment is going to be equal to F cracked multiplied by I times C. Why is that? Where is this coming from? I'm going to say because this says here F, the stress is going to be equal to M times C divided by Y. The stress in this case is going to be the bottom stress, the 474. So this is going to be the stress. The moment is what I'm after, what I'm trying to calculate out. C is going to be the bottom distance. What's the bottom distance? The 15.33. I'm going to take you here back for a second. This is going to be this distance from here to there, 15.33 to the bottom stress. And this is going to be your Y distance. This is going to be your C distance. My apology. This should have been MC divided by I, the moment of inertia. Now your moment of inertia is going to be this value here that we were able to entertain it and find out this area here. I can take this equation, rewrite it. I can say moment equals F times I divided by C, which is this equation here. The stress 474, moment of inertia 9840. From where? From this analysis, divided by the bottom side, which is 15.33. End up with exactly the same moment. End up with 304 kip inch. Very similar to this one, but this looks like an easier approach, right? The Flexural Formula, much shorter and easier. This one here, it takes time. But the good thing about this method, that you have something that you need to draw and understand. So it has more physical understanding. You know, when you have the forces, you have three forces, and then you have here the force. So here, you're going to be doing like 3D picture, and you have more understanding. When you do the analysis, you don't really need to develop this. This is going to be enough. If you just do this like 2D diagram, is going to be much simpler. You don't really need to do it this way in your analysis, right? So it seems to me that using this method is going to be much easier, the Flexural Formula. It is going to be a good thing if you can develop your own spreadsheet for this. So you're going to have here a T section. And once you have the T section, you can figure out the depth of the neutral axis, right? Which means this depth here, the 1533. And then you can figure out all of this. So try to make this as a variable. Flange width, flange thickness, stem depth, stem thickness, right? And based on this, once you put these variables, your spreadsheet is going to be able to find out your Y bar. And once you do this, also your neutral axis is going to be found to be in the stem. Then you're going to start to do all the stress distribution. Say if top is going to be this much, if bottom is going to be this much, if at bottom of flange is going to be this much, right? And then find out the forces, the three forces, and find out the tension force, right? And then find out the cracking moment. So it's going to be fun. You can do it with the compression force method, or you can do it with the flexural equation method, with this method here if you want to. Questions? I'm done for the day. So if you guys have any questions, let me know. try to assign the homework today. So if you like to start to practice, you can work on it. Good thing about the spreadsheet, you can double check your answer quick, and while you're doing it, you're thinking about the problem, how it works, right? And then you can back check this example, and then when I give you a homework, and you can do it with it quick and confirm the numbers, but of course, when you submit your homework, you need to show steps. So you're gonna have your spreadsheet handy, you're gonna have all the stress values and everything, and then you say, here's the value, and this is gonna be based on this, right? So it's gonna make your life much easier. Any questions? You're good? Yeah.
Good so far, but are you gonna post the question that you say you're gonna post?
Yeah, I'm gonna post it, but I want you first to work on the spreadsheet.
Oh, I'm sorry for that.
Yeah. I want you to work on it and just be open that dimensions can be just any given dimensions, right? And if there's gonna be a rectangular section, can you use the same spreadsheet for a piece section to solve a rectangular section? You say yes. Let's say the depth. This I'm gonna give you here a section, and this section is gonna be a rectangular section. It's gonna be like 16 by 24 or 25. I decided to make it 16 by 25. So in this case, when it comes to the top section, your top section, the width of it, you make it 16, and the bottom section, you make it also 16. For this depth, you can make it 5 and 20, right? Then you can back check where the centroid is going to happen. You say centroid is going to happen at 12 inch, 12 and a half from the bottom, right? So you back check your spreadsheet, and you see your spreadsheet is working fine when it comes to figuring out. Yeah, spreadsheet means Excel. Yes, create, yeah. And I'm really suggesting this. I want you guys to do it. Don't try to do it from online. I'm not looking for that. I want you guys to generate it, because by the time you generate your spreadsheet, you're gonna learn the subject totally 100%. I don't want this just to pass by, and then everybody later on is gonna be asking, yeah, we learned about crack moment, but we don't know what's that about. It was not clear, we don't know how to do it, this is tough. I want you guys to entertain this idea and just do it. It's gonna be very useful when you do an Excel spreadsheet, default spreadsheet, Excel spreadsheet, right? Because there's other software that you can make a spreadsheet with it. Yes, Angel, what do you mean? If you can explain, please.
Because Jorge said that is there some spreadsheets online, but I said there probably is.
Okay,
but
I see. You're
the
answering.
purpose
Okay.
is for us to
All
make
right.
it. Yeah.
Yeah, spreadsheet. I don't know, Michelle. What do you mean by we just like the formula? Yeah. Yeah, spreadsheet, and then you put the formulas in there. So for example, you say here's the first section, say for example flange, right? And then stem. You see the width and the depth. So the first one, if I'd like to do it, you say the flange is gonna be 20 by 4. And the stem is gonna be 20 by 5. Based on this, I need to do the moment of inertia. So I'm gonna say Ix for each one of them, plus this time the width of this, the stem is gonna be 5 by 20, plus the width times the depth cubed divided by 12. And copy this, and then add them together. So this, for example, Ix only, Ixo if you like to call it Ixo, right? If you like to change this, at one point you make this 6 inch, all numbers gonna get changed. Yes, Ramsey, you need to generate it. You need to build the equation to be able to answer the problem. Yes. This is great, but I want you guys to stay focused with me. Great, you guys have a good night. So you can sign out if you want to. Go ahead, sign out, and you can leave if you want to.